It's Math here. It's a great day for chemistry or physics. Sorry, guys, I'm not here to see you today. I had to go out of town, but I want to make sure that we're still on pace for our test, which will actually be the last day next week. The way the schedule is working out is it looks like we've got the makeup day for yesterday, Thursday. That makeup day is actually Monday. So Monday we're going to have a D day, which I will see you guys. We've got a D day, and then I think we go AHHE. Um, those H days are not going to be good test days. So unfortunately, next week I do see you. Well, fortunately, I do see you 4 times, but unfortunately, the middle two are H days. So it looks like we're going to go ahead. I want to go ahead and push today with capacitors and capacitance and give you this maybe this lesson so that you're on track. Help you out with the homework. You'll have a few problems on AP Classroom to do between now and Sunday night, so that we can talk about them on Monday, which will be a D day. And then we've got 2 H days kind of to review. I guess that's kind of good. We have short periods. We can go ahead and just review. There won't be any homework those periods, and we'll take a test on day 4, which is for us, which is will be going to be next Friday. So it looks like our electrostatics test will be next Friday. Okay, so I hope that helps. And here we go with capacitors. What is a capacitor? What is capacitance? Um, this will set you up for the AP classroom problems. I think there's about 15. So a capacitor stores charge in its electric field. It stores charge, stores energy using charge, but stores energy in an electric field. And so capacitance is the ability to do that. So like the flux capacitor, what is he trying to do there in Back to the Future? Is we're trying to store up a certain amount of charge and release it. And this is a great segue into circuit analysis. We haven't dealt with capacitors and circuits. We've dealt with resistors in series and parallel. You guys remember all the combination circuits and Sudoku physics. But what is a capacitor? So maybe you've ever charged like an old flash camera. You hear this little winding, this little, and then it sends a lot of energy quickly. Capacitors are almost like water towers, water tanks that can fill up, and they fill up kind of slow, but they can discharge real quick. Fill up and discharge, fill up and discharge. They store energy in the electric field. What they do is they store charge on plates. So imagine you had uh, a circular plate. So like a circular plate, and then you've got another one. And if I hook this to, say, a battery, and this is the positive end, this is the negative end, what's going to happen here? Now, obviously, there might be some more things in this circuit, but when I do this, when I connect this side is going to become very positive, and this side is going to become very negative, because that's the negative end, that's the positive end of the battery. And when I do that between these two plates, I'm going to start to get this electric field. And the electric field has energy. It has the ability to drive electrons if I need to. What actually drives electrons through a circuit? I think we talked about last year, even maybe if I were to kind of cut this wire and look at it, a piece of wire that's connected to a positive or negative um, in a battery. If I look at the wire itself, the wire connected to positive to negative has a field running through it. And that field is what drives negatives from negative to positive. The current starts flowing through there in the opposite direction of the field. So field flows from positive to negative. In AP Physics 2, we're going to start to understand a little bit more about what's actually happening with current. We know current goes from positive to negative, but does it really? The field moves in the wire from positive to negative, the electric field. The electrons then begin to precess against that. Okay? This is coming. All we're talking about today is you've got this thing called a capacitor. which essentially is two charged plates, even though sometimes they look like a soda can. And I'll explain why they do that in just a second. And if this one plate is positive, this could be a square plate capacitor, and this plate is negative. You would get this field between these two. And that field has the ability to drive charge. There's energy within that field. And I'm going to give you a few equations for the energy within that electric field. Okay. So first off, capacitance defined. How much energy can this thing store? Or what defines capacitance? Capacitance is a little thing called K E naught A over D. This K is not Coulomb's constant. It's a funky little K called the dielectric constant. Almost like mu for friction. Different materials have different constants. Air has a dielectric of 1. And a dielectric is something we put in here. I'll explain why that is in just a minute. Epsilon naught is 8.85 times 10 to the negative 12. And then D is my separation distance between the plates. A is a plate area, one plate area. Now, like anything in physics, this first time that we're learning capacitance, it's going to be like, well, wait a minute. What are you even talking about? What's going on here? Okay, just let it soak in as best you can, and it won't be long before this becomes kind of second nature too. It's not bad. We just need a minute to kind of get going. So like if this were my capacitor, these charged plates that can drive charge through a circuit, and this is just a circuit element. But it's part of electric fields because electrostatics, because I don't need charge moving yet to have the energy on in this electric field. So I've got these two plates. They're separated by a distance d. Plate area is the area of just one plate. So there's area. So doubling the area doesn't mean adding the bottom plate. I have to have the bottom plate. It's basically how much area you've got field moving through. So I just need the plate area of 1. How much area you've got field moving through. So that's area. Separation distance d. Epsilon naught is a constant. So what is K? Here's the deal. You can see with this equation, oops, going back to it. You can see with this equation, that's a constant, A over D. The bigger the area, the bigger the capacitance, the ability to store charge, store energy in the field. The bigger the area. That makes sense. If I have a huge area, I can store a lot of charge on those plates. If the distance between them is really, really small, then I've got a really strong capacitance as well. This is very much like lightning. What happens in a storm? The cloud becomes very, very positive, or excuse me, very, very negative on the bottom. Negative. We can talk about this later if you want. The top of the cloud becomes very, very positive, but the clouds are very, very tall. The ground starts becoming very, very, very positive as electrons get pushed away from the surface of the ground. So as electrons get pushed away, the ground becomes very, very positive. Well, check it out. I've created a capacitor. Positive to negative. I got an electric field that's moving from ground to cloud, a very strong electric field. And the bigger the area, or the closer this gets, the stronger that field's going to be, the more energy there is there, right? But what's eventually going to happen? If the negative and the positive get too close together, just like the Van de Graaff generator, when you get too close to the ball, it jumps. The negatives are going to ionize, well, the air ionizes and you get a lightning bolt, right? You get a jump, arcing. Maybe you've ever like jumped your car. If you get those cables too close together, they'll start to spark, or if they touch. If you get too close together, the electrons can jump from one to another by ionizing the air. So what the dielectric is a material that you can put in here that allows the field to still move through it, but prevents negatives from jumping to the positive to kind of neutralize the positive. What's the point? We're trying to store a lot of charge on these two plates, conducting plates, but they're not touching each other. We're just storing positive, well, negative on one and a deficit of negative on the other. We've removed negatives from one side, we've added negatives to the other side, we've created a differential. And we want a huge area and a small separation distance. Sometimes, if they get too close, the electrons will jump. So what we can do is put in a K, a dielectric, a material in here, like oil or some other material that allows the electric field to move through it, but it doesn't allow electrons to jump across it. Kind of cool. Dielectric constants are maybe 1 or 2 or 3. And all that does is if it's dielectric constants 2, it just means you have twice the capacitance. 3 times the capacitance. So what might you see for the homework? Okay, you've got a circular capacitor like this, circular plates, pi r squared. If you doubled the diameter of one, well, both, if you double the diameter of the plates and you half the distance, how many times have you increased or decreased the capacitance? If you double the diameter, half the distance between the two. Well, let's be careful. If I double the diameter and it's pi r squared, that's actually 4 times. Twice the diameter means twice the radius, but 2r squared is 4 times the area. If I half the distance, I'm dividing by half, so that actually would be 8 times the original capacitance. 4 times because of the area. I doubled the diameter, 4 times the area, half the distance, it goes up. Kind of makes sense. If I double the distance between the two, the capacitance would go down. If I add a dielectric, well, dielectrics are really easy. If you add a dielectric of 3, it's 3 times bigger. Take a dielectric out, it's less. Be a little bit careful with area. So capacitance is directly proportional to the dielectric constant, the area, but inversely proportional to the distance between the two. Cool? If I double the area and double the distance between, it's the same capacitance. But if I doubled the diameter, that'd be 4 times for a circular thing. Make sense? Okay. What other equation is super useful for capacitors? V equals ED. How strong is the electric field in there? Well, if I know that it's, say, 20 volts, and maybe this is only 3 millimeters apart, that would be my E. So if I ever need to solve for the electric field between the capacitors, voltage and separation distance are super useful. Is that okay? So this equation is awesome for capacitors. This is capacitance defined. Capacitance is actually defined by its geometry, the plate area, what's between the plates, how far the plates are apart. Okay, so there's 2 equations that are really useful. What about one involving charge? Q equals CV. Charge, this is confusing because charge is Q, and C is capacitance. So I didn't write out this one. You should already know this one though. Voltage, field, electric field, and separation distance. Is that okay? So you've got a few equations going on. You got your voltage equals field times distance. You got your capacitance defined. That's capacitance defined. And you got this guy. So this is kind of cool. If you know the capacitance and you know the voltage, you know the charge. How about one more equation? Energy. We talked earlier about the ability to store energy. And then I'll do a few examples. So the stored energy in my capacitor is 1/2 CV squared, almost like kinetic energy or something. This is capacitance and this is voltage squared. Cool. That's energy in joules. That's how much energy I have stored in my capacitor. So I'll do a couple examples to kind of get you guys going on these. And I think we'll be in pretty good shape. Cool. Okay. I think we're in good shape here. Ready? You can always go back and watch some of this if you need to. Okay, so I've got a parallel plate capacitor, has a diameter of 5 centimeters. So this is a circular parallel plate capacitor, diameter of 5 centimeters and separated distance of 4 millimeters. And air is between the plates. What's the capacitance? And I'll try to get out my calculator here for this one too, if I have it. Let me see if I have my calculator for you guys. Yeah, I think I got it. So determine the capacitance. Ready? So capacitance is K E naught A over D. K is going to be 1. That's not, again, Coulomb's constant. That's my dielectric constant. On your data sheet for AP Physics 2, it's kind of a funky little K. It looks a little bit different than the K that we would use for Coulomb's constant. 8.85 times 10 to the negative 12. That constant's called epsilon naught, the permittivity of free space. It's how an electric field moves in space. It's kind of cool how electric field saturates space. And then because it's circular, my area is going to be pi r squared. So if the diameter is 5, the radius is 2.5, but that's centimeters, so 0.025. I gotta be really careful I don't make mistakes here with decimals and all that kind of stuff. Over 0.004, and there's no squared on that distance d. Okay, so let's see what we got here. 8.85, calculators unite, 10 to the negative 12 times pi. Let's see if I can find my pi. Where did I put my pi? Times 0.025 squared divided by 0.004. Okay. Let's see. 8.85 to the negative 12. Yep, that looks good. 0.004, because 4 millimeters is really close. So 4.34, 10 to the negative 12. And that's measured in farads. What? Capacitance is measured in farads. Capital F. Almost like force, but we'll call it farads. So what would this be? Pico, like 4.34 picofarads. Right? Pico would be 10 to the negative 12. Is that okay? So capacitance is a little bit funky. Um, let's continue on. The capacitor is connected to a 20-volt source. Determine the following. So now that I know the capacitance, what else could happen here? Determine the following. How about the the electric field? or B, the charge stored on one plate, or C, the energy? So here's some more things we can look at, okay? The electric field between the plates. So if I want the field, I've got voltage. This is going to be V equals ED. That's a great relationship for voltage, separation distance, and field. So in this case, 20 equals E times 0.004. So still we're using a lot of the same, not a lot, we're using V equals ED, we're using some of the same concepts as before, but we are adding in this thing called capacitance, which will be a very useful element when we start doing circuit analysis in a week or so. So 20 divided by 0.004, and I find that that's 5,000 newtons per coulomb. 5 times 10 to the 3. Cool. So there's that. What about the charge stored on one plate? That's Q equals CV. So you talk about charge with capacitors. Charge is Q equals CV. So my charge is going to be equal to, Q is going to be equal to C. This is a bit of air carry forward here. 4.34 10 to the negative 12. So it's going to be pretty small here, times 20. So 4.34 times 10 to the negative 12 times 20. And I get, goodness, I can't see, 8.64 10 to the negative 11. Yeah. Sorry, the light's a little bit bad here. 8.64 times 10 to the negative 11 coulombs. So, okay. Good so far? How about the energy stored in the capacitor? 1/2 CV squared. So one reason I like, we're adding this kind of towards the end of electrostatics is it's not anywhere as near as difficult as field and force and potential and some of these other concepts. It's just adding a few things. And it's got these a la carte equations. What's the energy? 1/2 CV squared. What's the charge? CV. So pretty easy relationships here. So equals 1/2 4.34 times 10 to the negative 12 times 20 squared. 4.34 times 10 to the negative 12 times 200, because that's half of 20 squared. 8.68 10 to the negative 10, maybe. So really, really small. It's hugely small amount of energy. Okay, cool. But it doesn't take much energy to drive electrons either. So there's kind of capacitance 101. You might get something like, let's talk about this relationship right here. First off, we okay? Got it? Good. Okay. You might get something with this relationship. If a capacitor is charged, you may see this in the multiple choice concepts. What if I charge a capacitor? If I charge a capacitor and then I slide a dielectric into it, what happens? What in this relationship? Charge must be conserved. So if a capacitor is charged, it has a certain amount of charge on it. That's what it's got. So if I then took the capacitor and slid a dielectric constant in there, what would happen is that the charge would stay the same. But by the dielectric constant going in there, the capacitance goes up. What would that mean about the voltage? It would actually go down. And that's really, really weird. If I charged the capacitor, moved it over here, slid a dielectric in, the voltage would actually go down. Really funky. But that's because I can't add charge. I can't add charge, but I can affect the capacitance, which actually would affect the voltage or the potential between the two. If I had a charged capacitor and I removed the dielectric, so the capacitance went down, so now the capacitance going down, the voltage would go up. So I put the color code to see. And that's if the capacitor is charged, because sometimes College Board, they'll give you these relationships like Q equals CV. What happens if I increase voltage? Well, if you increase voltage and the capacitor stays the same, the charge goes up. If you increase voltage, the capacitance stays the same, the charge has to go up. But what if what if you're just separated out and the charge is not being changed, and I change the capacitance? Well, then the voltage may go up or down. Is that kind of okay? So you got to think. I've seen questions that involve understanding the relationship between charge, capacitance, and voltage. So just be a little bit careful for these. Hopefully that little discussion will help you as you approach some of these. And of course, gang, we've got extra time actually now next week. Instead of taking the test on day 2, which is an H day, we're going to take the test on our last day of the week. So you've got this lesson, you've got some problems to do on AP Classroom by Sunday night and the rest of this period. We're going to go over those on Monday. Then we've got open days on the 2 H days, I believe Wednesday and Thursday, and then testing them will be on Friday. I hope you have a great weekend. Be safe. Take care. God bless.